I believe that's the signal I can start. So welcome. Thank you all for coming to this talk, which is going to be about Scala.js and specifically its semantics, in the sense that it's fundamentally a dialect of Scala. It has some specific semantics that differ or that in addition to Scala on the JVM. And I will focus on the aspects of these semantics that support a good interoperability with JavaScript libraries, code, the DOM, but also your own code. And also on the aspects of the semantics that allow us to compile it to efficient JavaScript, if such a thing exists. So compiling to JavaScript is such, this is an old problem. There are literally hundreds of languages that compile to JavaScript at the moment. So you have, even some languages have even several dialects of their own, each compiling to JavaScript with each its advantages, disadvantages. And then there are other more languages that inherit or inspired by some of the languages. I think one of the existing languages that has the more prolific ecosystem of dialects and such is Haskell. I think there are at least 5 dialects of Haskell compiling to JavaScript, and then a couple more languages inspired by Haskell and compiling to JavaScript. It's quite huge. So basically, at the moment, languages that do not compile to JavaScript are the weird ones. Basically, all the mainstream languages you know, and many languages that are not mainstream and that you do not know, all of them, they compile to JavaScript. JavaScript is not, it's basically, it's a platform. It's just like x86. So compiling to JavaScript is such, this is a solved problem. Everyone does it. So what's hard? So in my opinion, there are two things that are hard, and which is the topic of this talk. It's interoperability with JavaScript code. So a lot of languages compiling to JavaScript, it's really awkward to talk to existing JavaScript libraries. In most of the cases, you actually have to embed strings or comments in the host language, which happens to be JavaScript code, and then you have to somehow know how identifiers and types match between the two. And in some cases, the best you get as documentation is look at what the compiler generates and kind of imitate that somehow. So I don't think this is acceptable. And I wouldn't say from day one, but certainly from week 3 of the development of Scala.js, it became clear to me that this is the one thing I have to get right. Performance came much later. In the beginning, I didn't believe we could reach decent performance with Scala.js, to be honest. It turned out to be relatively okay. And that was without even beginning to do any optimizations. And then I started doing optimization, and suddenly it became crazy. We're within 2x of JavaScript most of the time, and actually more on 1x of JavaScript. So this is all because of the way the semantics of this dialect of Scala are defined, so that we can have both these things. So because we're talking about Scala, about semantics, and everyone loves a what moment, so we were going to have some crazy examples of the semantics. So let's talk about JavaScript. So this is a pretty famous example in the JavaScript community. You would of course expect this to give you an array of 4 numbers, which are 10. Well, guess what? You get this. So how can that be? Well, let's desugar the map. If you desugar the map, you actually get this. So map will actually give 2 arguments to your function for every element. It will give you the element itself, but also the index. And then the thing is, parseInt, because in JavaScript you have runtime overloading, it interprets the second argument as the base in which to interpret the number. So, and it defaults to 10. So 0 basically means 10 by default. Then 1, it doesn't make any sense for a base 1 that doesn't exist. So that's 9. Okay, that's reasonable. And then if you interpret 1, 0 in base 2, well, you get 2. And that's how it works. So if you want to fix this, you actually have to include your own lambda in there. This, by the way, is completely valid JavaScript. Well, it's valid ECMAScript 6. So this is the new JavaScript, which got lambdas a la Scala. That's quite wonderful. So you can fix it that way, because then your lambda acts as a bodyguard against this second argument that you don't want. So it's all good to make fun of JavaScript, but we can also make fun of Scala. Right? I think the Scala puzzlers is a good example of these things. And this is a pretty well-known one. I have just adjusted a little bit. So we create a new array with 3 elements. They're initialized with null, right? Because arrays are initialized with null elements. And then we convert that to a set. And what does that give you? False. So how that can be? Well, the thing is, if you remove the parentheses, then you get what you expect, a set with the element null in there. And the thing is that Scala will actually add a call to the apply method, because you did add the parentheses and you were not supposed to. And then because you call the method with 1 argument, with 0 argument, it inserts unit, because, well, that's what it does. This is deprecated, by the way, but it still works. So if you have JavaScript with semantics and Scala with some puzzlers, imagine what we can do with Scala.js. Let's amend a little bit the previous example, and instead of creating a Scala array, we create a JavaScript array. So you may know that if you create a JavaScript array, it's not filled with nulls, it's filled with undefined, or to be more precise, with holes, which most of the time are interpreted as undefined. So what do you get if you run this? True. So let's do the same exercise. Let's remove the parentheses, right? And then you get what you would expect, right? A set with the value undefined in there. Because, well, we're in JavaScript, right? So undefined, that's a real thing. And so does that mean that unit is undefined? Well, yes, it is. So this is one piece of the semantics of Scala.js that can be confusing at first, but that actually are immensely important for interoperability with JavaScript, which is that unit, the value unit, is actually the same thing as the value undefined on JavaScript. Because if you think about it, when you write a JavaScript function that doesn't return anything, it will return undefined. So it just makes sense. Okay, that's all about the fun stuff. Let's get down to business now and into the real stuff. So we'll cover quite a few topics about these. So first, we'll talk about the discrepancies with respect to the semantics of Scala on the JVM. So in the sense that if you write the same code and you cross-compile it, it might behave differently if you run into these cases. And then we'll cover semantics that are added to the dialect so that we can support interoperability. And I have a small section about what this enables in terms of optimizations. So the first thing that is different on Scala.js and Scala JVM is primitive data types, and especially numbers. You might know that JavaScript has only doubles, basically. So it has a number type, but it's all specified as doubles, which is great to encode Scala doubles, but not so great to encode all of the other numeric types. In particular, long, because long, you cannot even fit a long in a double, no matter how hard you try. And character is also a numeric type, but it's also weird because, well, it's toString, doesn't give a number, so it's a bit annoying. So let's talk about ints first, because it's probably the data type that you use most in your programs, even if you don't realize it. So even though JavaScript doesn't have an integer data type in the language itself, actually the JavaScript VMs, they do have integers because they optimize your program based on runtime profiling and stuff. And they discover, oh, but this number, it's actually most of the time it's a 32-bit signed integer. That's all I've seen so far. So let's optimize it as such, and then insert guards in case that doesn't work, right? And there is another thing. It's that there are some operators in the language that forcibly convert their operands into signed 32-bit integers, and in particular the bitwise operations. So when you have these bitwise operations and you know a little bit about the modulo 32 arithmetics, you can encode all the operations on Scala int so that they will behave in the correct way on a JavaScript VM, in the sense that it will wrap around the 32-bit boundaries. So this is how you do it. So a plus b becomes a plus b binary or 0. And you have a lot of other stuff. Multiplication doesn't work quite so well, so they did introduce a new function in ECMAScript 6 that does it. But you can polyfill it. But don't worry, your browsers have been implemented IML for quite some time now. So that's all and good. With this, Scala.js can give you the proper, in the sense that same as on JVM semantics for ints. But then what about the performance, right? We have this additional bitwise binary op, which is quite annoying on the eye. It's annoying for the human, but it's actually very helpful for the VM. So actually, on modern VMs, on the desktop at least, a plus b binary or 0 happens to be faster than just a plus b. Because the VM can recognize that this is a signed 32-bit addition, right? So it will optimize it away as such, which is quite good. So now Scala.js gives you true, in the sense of same as on the JVM, and efficient ints on the JS platform. More efficient than what you would write by hand, because let's face it, if you write JavaScript by hand, you will never introduce this binary or zeros all the time, right? So for the other numeric types, I won't go into so many details, but this is the summary of it. So you also have correct and fast byte sort chars and doubles. Then the longs, they're correct, but they're implemented with a class with methods for all the operations, so they're quite slow. So if you need performance, avoid longs at all costs. And then there is floats, which is the other way around, because most of the time you don't really need floats to get truncated to 32 bits all the time. So by default, they behave mostly like doubles. But you can have opt-in strict floats, and then you get the correct semantics. But then again, they're very slow. At least if your VM doesn't support the fround function. On another related topics, still about primitive data types, you would really like not to box the primitive types, right? Because, come on the JavaScript is a dynamically typed language. You don't want to box an integer into a Java long integer just because you want to put it in an any or in a list or in a JavaScript array for that matter. So you really don't want to do that. And Scala.js doesn't do that except for characters, for weird reasons I won't go into details today. But to do that, we need to change a little bit the semantics and accommodate for that change. So first, we need to be a little bit more relaxed about toString on primitive types. And especially on doubles and floats, you will not see the .0 that the JVM would print. OK, that's fine. And unit, if you call toString on it, you get undefined. Because as we saw earlier, unit is undefined. It's the same thing. And there's another one which is sometimes a bit annoying, but most of the time is fine. It's the instance tests. So you'll say, oh, but I never do an is-instance stuff in my Scala code, right? Why would I do that? There is pattern matching. Well, the thing is pattern matching does use is-instance stuff, right? So then it will change in the sense that the test will answer true if the value could be a valid value for the data type that you test. So if you ask, is 1.0 a byte, it will tell you true, because it's a valid value for a byte, right? And this is necessary. We will have to relax this, because if you don't box the numbers, well, all the ones of all the data types, they all became the same one of JavaScript, so you cannot distinguish them after the fact. So this is something we have to relax compared to the Scala JVM semantics, so that we are allowed not to box. And of course, this is great for performance. A completely different topic, we're done with primitive data types, is undefined behaviors. So, class cast exception. If you do an invalid cast on the JVM, the JVM is I mean, fundamentally it's a bug, right? I mean, you messed up. Let's face it. So, but the JVM is still very nice to you. It will specify that, oh, no, don't worry, I'm going to throw this particular class of exception. You won't have weird behavior happening before or after this. It's all nice. You get your exception. And sometimes people rely on this, and they shouldn't. So on JavaScript, of course, there is no such thing as a class cast exception, because there is no such thing as cast, because there is no such thing as a static type. So if we want these class cast exceptions on Scala.js, we have to encode them with regular compiler emitted code. And this compiler emitted code is a bit verbose, it's not trivial, and of course the JavaScript VMs has no idea what it means, in the sense that it cannot optimize it away the same way that the JVM optimizes away casts. And believe me, the JVM is doing an immensely good job at optimizing away the as instance offs. So it's quite annoying. And it's so annoying that you can get up to 100% overhead on your program. So let me repeat this. Your entire program becomes twice as slow just because you check the as instance offs on Scala.js. So this is not really acceptable. So what we do is we declare this is undefined behavior. So if you do an invalid cast, basically the implementation of the Scala.js language is allowed to say, bah, I don't care, you messed up, this is all your fault. I'm going to do arbitrary stuff. So it can really do arbitrary stuff. It will do arbitrary stuff. And that's even without the optimizer taking advantage of this to decide, oh, but that cannot happen over there, so let me optimize before, because it can backfeed itself some information. So this is the kind of things that C compilers, they do, and C++ optimizers. We don't do yet many optimizations based on this, but we could. But either way, what's going to happen is that your program will continue with the value that doesn't have the right type. And this is not good for debuggability. It's really hard to first figure out that there's a problem, and then even if you do figure out that there's a problem, where did it happen? It could have happened earlier in your program and you have no idea. So, because we don't want to sacrifice the debuggability of Scala, we have basically two modes. We have a development mode and a production mode, which, if you know Scala.js, is what we refer to as fast OPT and full OPT in most of the time. So in dev mode, you will get the checks, and in production mode, you won't get the checks. So by default, in development mode, you are in the fatal behavior, and it will do the checks, but you won't throw a class cast exception. Because imagine if it does throw a class cast exception, and you rely on this, then it becomes broken when you go to production, so you don't want to do that. So instead, it throws an undefined behavior error. And this class of exception, it's actually a class of error, because it's a subclass of error, is considered fatal in the sense that it is not caught by a case non-fatal. So this exception will blow your program immediately with a proper stack trace, or as far as a JavaScript runtime can give you a proper stack trace. And you can, that way, debug your program effectively. Then when you go into production, you receive the unchecked behavior by default. And the unchecked behavior will just say, oh, I don't care. I mean, it cannot go wrong, right? Because it's undefined behavior. So if it does go wrong, you messed up in the first place, so it's your problem. So let me just do a no-op here and continue. So then you get performance. And then if you really want to be portable, you can ask for it. And this is opt-in and applies to both development and production. And then you get a proper class cast exception exactly the same way that the JVM would give it to you. And that provides portability if you really need it. But I would advise against it because it will make your programs much slower. There are a bunch of other classes of exceptions that we consider undefined behavior in the same way. To be noted is null pointer exception and the index out of bounds exception. Eventually, most of those, the start ones, they will also have this unchecked, compliant, fatal settings. But for now, they're all unchecked just because we've not implemented the checks yet, but it will come. Okay, that's about it for the differences with respect to Scala JVM. So other than that, your program, as far as the Scala language is concerned, behaves exactly the same way on Scala.js and on Scala JVM. So everything else, if your program satisfies these restrictions here, it will behave the same on Scala.js and on Scala JVM. I'm talking about the language here, so that doesn't mean that you can call into an arbitrary library such as Java long threads and expect that to work, okay? So this is another thing. I'm talking about the Scala language as such. Okay, let's move on to JavaScript interoperability and the semantics that we add to Scala.js to be able to talk to JavaScript in a natural way. So from now on, most of the codes, it wouldn't even compile on Scala JVM because it doesn't have the types. It's not part of the standard library. So there is no such thing as portability or behaving the same as on Scala JVM because it wouldn't compile in the first place. So I hope this is readable until the back. I think so. I made it quite big. So this is the kind of code that you would see possibly in a Scala.js code base. So this is mostly Scala code. It very much looks like Scala code to me. But it deals with a data type, which is an XML HTTP request, which is, you can see it in the DOM namespace. That's just to make it clear. And it's fundamentally the XML HTTP request class in the browser. It's the one, the JavaScript thing, right? It's not a wrapper. It's not anything. It is the XHR from the browser. And then we instantiate that thing with new, and then we call methods. We pass in strings. Much better. We store a Scala lambda in there. Fine. That's a JavaScript function. I mean, yeah. And then you can call methods, read fields, write fields. You basically work like if it were Scala code. It's just you're talking directly to the JavaScript library. And this is all statically typed, of course, because we love that. So how is it statically typed? Well, because there is a definition of what XML HTTP request is as a library, and it is basically a class with methods, fields. And the thing is, since it's a JavaScript class in the first place, you make it extend from js.any, which is a special type in the Scala.js compiler. Actually, it indirectly inherits from JS.any, hence the dots there. But basically, everything that inherits from JS.any, the Scala.js compiler knows, oh, okay, this code is not mine. It's not Scala code. It's just there for the types. I won't emit the code for this class. It's irrelevant. You can see that actually we put JS native pretty much everywhere just to tell the Scala C, the type checker, don't worry, this is not an abstract method. It is implemented. It's just it's in JavaScript. So the code for this class disappears at runtime, And also the compiler knows, okay, but when I manipulate this class, I'm actually manipulating a JavaScript object. So I had better talk to it in the way that JavaScript would talk to it. And in the way that you have a correspondence in terms of syntax most of the time. So what does that mean? That the syntax, that the corresponding syntax? Well, that's where you have to go to the semantics of the language and look, oh, when I do syntactically or semantically in Scala.js code, new of foo being a JS any class. If it's a Scala class, well, then it's just a normal Scala new. But if it's a JS any class, or how we call them, a raw JS type, then that means, in terms of the semantics of JavaScript, that you're selecting from the global object of JavaScript, you're selecting the member foo. You expect that to be a constructor function, because in JavaScript, a constructor is actually a function that will create your object. And I pass in the arguments one by one. And then method calls, it's basically the same. I mean, we're very lucky with Scala.js because syntactically, Scala resembles a lot JavaScript. So most of the time, you can interpret things basically the same way just by syntactically translating. But you have to understand that this is not, it's not transpilation in the sense that it looks at the syntax and turns the syntax around. It does understand the meaning of the program and compiles it. So you can notice that I have two instances of the open method here, but in the definition there's only one. It's just that it has default parameters, and for example, default parameters will be translated to the JavaScript notion of default parameter, which is not putting the parameter instead. Same for variadic arguments or star, and a lot of other features that basically go beyond the scope of this talk. But basically, it just works. That is what you should typically remember from this. So this is what enables you to write this kind of code and really understand it the way that the Scala language tells you, but in a way that will manipulate a JavaScript object. And this is one of the most important bits about great interoperability with JavaScript code, because you just do it, you just call them. I mean, you just call the JavaScript libraries and it just works. So with weights, there's a string in there. So I'm passing this string here to JavaScript, but we all know that a Scala string is actually an instance of Java long string, right? So how is JavaScript going to understand a Java long string? That doesn't make any sense. So this is why the language defines a couple of type correspondences between values in Scala.js and their data type in JavaScript. So it all boils down to this. So you only have those. In particular, you can see if we have a string, which is not null, so an instance of Java long string, it is a primitive string in JavaScript. It's not converted to a JavaScript string. It is a JavaScript string. So the language guarantees that if you write string, even Java long string in your code, it is actually a JavaScript string. And you have some other relations, for example, numbers and the famous unit undefined. So one thing to note here is that there is not long. Long doesn't behave that way. Car doesn't behave that way. And everything else doesn't behave that way. So all the other types, so instances of any other Scala class, which is not a raw.js class, is completely opaque to JavaScript. So if you give it to JavaScript, it will say, I have no idea what this is. I mean, all I see is an object. Okay, and I don't even know what fields it has or what methods I can call. Basically, it cannot do anything. All it sees, it's an object. So it can pass it around, store it, give it eventually back to Scala.js code, but it cannot do anything with them. In particular, Scala functions are not JavaScript functions, the same way that Java long strings are primitive JavaScript strings. So then, how did, yeah, you see here, I'm still assigning a Scala lambda to unload here. So then, for other data types that are not in direct correspondence, what we provide is implicit conversions. So we define a new type, which is js.function, well, js.function1, and we have 23 of those for all the arrays. And we have 23 implicit conversions in one direction, 23 implicit conversions in the other direction. But from a type system point of view, and the way you can understand it as semantics is it's an implicit conversion in terms of Scala. It's nothing special, except that the implementation of this conversion is a bit special. So this is compiler provided. The language promises you this, that this implicit conversion will give you a JavaScript function, call it G, such that if you call G in JavaScript, then that has the semantics of calling the apply method on Scala.js. So this is another direction, right? Before I talked about if you have this Scala.js code, it has this JavaScript semantics. This is the other way around. If you have this JavaScript code, it has this Scala.js semantics. Okay, what about embedding JavaScript code? I'm pretty sure this is unreadable, but that's not the point. So this was a Stack Overflow question. Asking, but wait, I just have this JavaScript snippet of code here on another Stack Overflow question. I mean, can I not embed it just in my Scala.js and be done with it? The answer is no. Scala.js does not allow you to do such a thing because it's a sin. It's a sin because there is no way you can relate stuff in a string, which would be JavaScript code, inside your Scala code. I mean, how would scoping resolve? How would the data types behave? It doesn't make any sense, right? So instead, Scala.js strongly believes that it shouldn't let you do this, and instead gives you all the semantics you need to be able to do it while staying in Scala.js. In particular, there is this apparently magical type, which is JS dynamic. If you went to the previous talk by Richard, he basically showed that with JS dynamic, you can talk to a JavaScript API without thinking about the types. You're actually writing dynamically typed code, and it will blow up at runtime and not at compile time if you mistype things. Another thing that I want to tell you is that we have this facade types, these raw JS classes and traits and objects. What if they're wrong? Because we wrote them so that they match what the JavaScript code would do, hopefully. But if they're wrong, do we trust them? So the compiler doesn't trust them. So the compiler, every time you get back a value from JavaScript into Scala.js code, it will cast it with an as instance of. Why? Well, for essentially one reason, which is, I would say, mostly performance oriented. Because if you cast it now, then after that, you know this is going to be a Boolean, say. And if you know this is going to be a Boolean, and there is no way it cannot be a Boolean because we've checked it before, then that means the optimizer can use this notion and can use the knowledge that this is a Boolean or an int or whatever to optimize further your program at will. If we did not do that, then every time we get something back from JavaScript, then we don't know anything. And then the optimizer is stuck. And this is why it's hard to optimize JavaScript itself, is because you have no static type information. So we force the static type to be known at that point, and then we're okay. Now the other direction. So if you have, now I've shown how Scala.js code can simply and elegantly talk to a JavaScript library. But what then if you want your JavaScript code to talk to your Scala API? Remember that I said instances of any other Scala class is opaque, so it can't do anything. You give an object to JavaScript, it does not know what to do with it. It cannot call even the public methods of this object. That doesn't work. The language doesn't give you this guarantee at all. Actually, it will try very hard not to let you do it because it's in undefined behavior if you do. So if you want to obtain to expose some of the parts of your Scala library to JavaScript, you use exports. And exports are simply annotations that you put on classes, on objects, on members, so val, vars, defs, and that tells the compiler, okay, I want this to be callable from JavaScript, make sure it is, and it, again, in a semantically nice way. So again, you can, if you export point, it will take the fully qualified name of point and put that in the global object, and that means you have this Scala.js semantics. And the same works for pretty much everything. Won't go into too much detail because it's basically the opposite direction as the facade types, the raw.js types. There is one standard export, it's Java long object toString, because it's just nice, because JavaScript also has this notion of a toString method. So you can do string concatenation in JavaScript and it will map to the toString method. Okay, so that's all for the semantics proper. I want to spend a tiny couple of minutes on optimizations that this whole thing as defined enables. So in Scala.js, we have a linker. So you compile your Scala.js libraries independently, but at the end of the day, you have to link the entire program using the linker and the optimizer to get one JavaScript file. At that moment, the optimizer knows everything about the Scala.js code, including the dependencies and transitive dependencies. It knows everything about the Scala.js code. It also knows that there is no reflection because Scala.js doesn't have any kind of runtime reflection. It has compile time reflection, macros and stuff, but no runtime reflection. So the only things that can be accessed in a reflective kind of way are JS exports, because you never know what JavaScript is going to do, but you know that it can only call exported stuff. So because you know all of this, you live in what we call in the optimizer vocabulary, we call that a closed world. This is a giant bubble in which all of your Scala.js is in the bubble, and you know that JavaScript can call in from there, maybe there, but that's all. Inside of the bubble, you can do everything. This is a heaven for optimizations. You know everything and you can do everything you want, so you can be completely crazy about your optimizations. Let's look at one or two examples, I think. So this is a fold left on an array with an accumulator, which is a tuple of integers. Inside, we have a pattern matcher, a pattern match, and depending on the player that's on the board, we will increase the relevant part of the score. And don't worry, you don't need to read it all, but just look, this is the translation, and basically, you have only local variables, a while loop, a couple pluses, and a couple ifs. That's all. So it's all gone. There is no lambda. There is no tuples. They're all gone. It's just local variables and while loop. That's pretty cool. And this is not because it's just array and the optimizer knows about array. No, it's very general. So it works with your code. So you can define this small code here, which defines a new method on int with an implicit class, which takes a lambda, which will call the lambda as many times as the integer so, for example, 3 times a block of code will execute 3 times that particular block of code. Okay, that's pretty. And this is the JavaScript that you get from this. So again, the lambda, it's all gone. All you have is a while loop. So even if you noticed, it's not even a while loop in there. It's a for comprehension over a range. It disappears. It's just a while loop. So this optimizer is quite crazy. And so this is what you get. I'll be a bit quick about it. What you have to look at mostly is the green bar. The green bar is Scala.js with its optimizer, and the blue bar at the bottom, that is JavaScript. So we've normalized to JavaScript, so JavaScript is always 1. And you can see that the green bar is pretty close all the time to the blue bar, except here, that's a benchmark making lots of use of the collections. And the Scala collection library, they're good, but they're just not as fast as a JavaScript array on the JavaScript VM, because the JavaScript VMs are crazy about optimizing their arrays. So we have another version of that same benchmark, just replacing all the Scala collections with JavaScript arrays, but otherwise using the same higher order methods just on a JavaScript array with the Scala collection API, because that's what Scala.js gives you, and then we're back. The black bar is if you add the Clojure compiler, and we've come to a point where the Clojure compiling is actually hurting our performance, because the Clojure compiler optimizes for code size, not really for performance. So you usually lose a bit of performance with Clojure. We will probably have to do something about that, selecting parts of Clojure that we want and discarding the ones that we don't want. And just to give you an idea of how much these optimizations that I talked earlier about are worth, well, look at the other blue bar, the dark blue. And this is if you don't run the optimizer. So the optimizer of Scala.js is really good. It gives you from 3 to 5 or 6x improvements over the code. And since Scala.js appears to be somehow from 5 to 10x slower than Scala JVM, it might be that you could craft a particular benchmark on which Scala.js would actually beat Scala JVM. I haven't done so yet, but I'm pretty confident I can manage to do one. But it would be crafted. It would not be a mega benchmark or so. Okay, so that's it. So Scala.js, well, first, it's Scala. I mean, the discrepancies with the semantics of Scala JVM are really tiny, and most of the time, really, they really don't matter. Usually, it's just Scala. Second thing, it talks to JavaScript. It can talk to JavaScript, statically typed way, dynamically typed way. Doesn't matter. It all works fine. And third thing, it's pretty fast. Thank you. So I think officially we have 2 minutes for questions. So feel free to ask on the microphone, preferably. Sorry, the acoustic is really bad. I really can't understand what you say.
Well, you mentioned that if something like a class cast exception occurs in your program,
yep,
then you get undefined behavior.
Yep.
So trying to catch, for example, a class cast exception, would that be a compiler error?
So if you try to catch a class cast exception, the compiler will let you catch the class cast exception that will never arrive. So it will instead, in development mode, throw an undefined behavior error, and then one will fall through and just give you the immediate crash. So you can write the catch for class cast exception, it just will never trigger. Yeah.
Right,
I mean, probably a linter could detect this and say, hey, look, this is never going to happen. Yeah.
All right.
I'm a bit biased because I'm actually a front-end developer, so
that's
it. I've seen various attempts, named Wicked, named GWT, to move to the front-end with Java or back-end related languages. But you get very nicely the 80%, and at some moment you will need to write JavaScript, right? Or how do you see that? How will Scala.js succeed where GWT tried also, but gets nicely to the 80%, but then people still need to go to a front-end developer to develop JavaScript, just plainly.
Well, precisely because you don't need to go to JavaScript. Because of the nice interoperability, you really can do anything JavaScript can do. So everything that you would be able to write in JavaScript, you can also write it in Scala.js. You don't ever need to go to JavaScript. You can if you want, but you really never need to. Scala.js really can do everything JavaScript can do, except double equal. It's triple equal instead. We won't let you do the double equal. So yeah, that's the answer of Scala.js. We give you all the semantics that you need to be able to talk to arbitrary JavaScript code, and you don't need to fiddle with weird hybrid things. Yeah. Any other question? Okay, anyway, I think the time is up. So, but I'll be happy to take questions afterwards. Thank you very much.